I'm going to begin just by going through a bunch of examples of what I would call easy factoring, all right? So let's and by easy, I mean we're just factoring out sort of one thing, all right? So these sort of problems are, less difficult than the ones we were doing at the end of last class, right? But they're important because this is kind of the first line of attack, all right? So here it goes. And some of these are in your homework. So today we'll be talking about factoring, all right? And of course, I mean factoring polynomials, that's pretty much what we factor. All right? So example. Here we have 8. I'm going to change the letters. 8x squared plus 4x. It's got an a in your homework, but I'll use x here. So let's factor that. So I would point out that we can write this as 4x times what? So let me ask you the question. Here's how we think through this. In order to get 8x squared, I take 4x times what? What times 4x gives me 8x squared? I need a 2 and I need an x, right? 2x. Right? And then what times 4x gives me 4x? 1. So I get this. So there you go. 4x times 2x plus 1. We factored it. All right? There you go. End of story. All right. Well, we could do a little bit more. All right? If you wanted to, you could factor out a 2. Now, this is a little bit tricky. How do you factor a 2 out of 2x plus 1? Well, the 2 out of the x, that's easy, right? But what do I have to put here in order that 2 times that thing gives me back 1? What's that? What did you say? 0.5, right? So 0.5, I'll take that. You could write also a half if you want, right? But that's how we do that. So you could also write this as 8x times x plus 0.5. And that would also be a good answer. In some sense, it's a better answer, all right, for reasons I'll talk about later. But example 2. Either one of these I would give full credit on the test, all right? How about this? And I'll use the homework's letters this time. A to the 4th plus 5a cubed. And by the way, this is from section 4.3 at the moment. And beyond. We're not to the beyond yet, but there we go. So here we go. What do you guys think? What can we factor out of this one? An a? Let's see here. How about, I think we can get an a cubed out of this one. And then the question to ask is, so I want something here times a cubed, which gives me a to the 4th. Of course, that's just a, right? Whatever I put here, that times a cubed must give me 5a cubed. So what do I get? I get 5, right? So there you go. Let's see here. Let me see if I can find another example. How about 10s squared minus 2s to the 4th? So let's see here. What's kind of the biggest, baddest thing we can factor out of this? I think we can get a 2s squared out of this, right? So 2s squared. So this, would you say, I heard a 5? Yeah. And I'll try to make my 5 look different than my s. There we go. I think I succeeded. I do not always succeed. That is a deficiency of my font, my native font. 2s to the 4th. How are we going to get that times something, 2s squared times something to give me minus, what do I got? Negative 1. Negative what? Yeah, negative 1 times s squared. I'll just write that as minus s squared, right? There we go. So now, so that's we have factored it. Now, I would put a comment here. This is not completely factored. Over the reals, all right? So we'll come back to this, all right? We're going to come back to this. It turns out the first two examples actually already, these are both completely factored. I could actually not factor those further, all right? Cannot be further factored. These are completely factored. So, do you see why that is? Like, there's no way you could break x down, right? There's no way you can further break x plus 0.5 down. That's as far as you can go, right? You can't split those into a product of two polynomials. A cubed, I mean, that's it. You can't, it's a times, I mean, that's already, you can't break that down into a product of two further smaller polynomials. A plus 5, you can't break that down further, right? But it turns out we can break down 5 minus s squared, all right? So I'm going to talk about that. We'll come back to this, okay? So example 4, what if we had x to the 4th plus 3x squared, plus 3x cubed plus 2x squared. Can you guys factor something out of this? I heard an x squared. So we do x squared, we got what? We got x squared times x squared plus 3x plus 2, right? So if I just said to factor, we could say that that's the answer, right? But if I said factor completely, we can do more, right? Do you guys remember? So let's do more. This x squared plus 3x plus 2, how can we factor that? I'll put a template here, x, right? And we notice that 2 is 1 times 2, right? It's also minus 1 times minus 2. We're looking for those numbers to add up to 3, right? We're looking for those numbers to add up to 3, whatever we put there. So we want to use what? Not minus 1 and minus 2, but the what? Yeah, add up to 3, right? Because we were trying to get 3x plus 2, right? So I suggest we got to put a plus 1 here and a plus 2 there. That's going to work out because 1 times 2 is 2, right? And we get the x plus the 2x, which gives me back the 3x. Using that guess and check method we talked about last time, right? Now there, we're done. That's completely factored. We can't go further, right? Example 5, if we had x cubed plus 4x squared plus 5x, right? Let's factor that. Can we factor something out? How about, we can't factor x squared out of this one, right? Because the last term just has x. So we can't get an x squared out, but we can get an x out, right? So we've got x times x squared plus 4x plus 5. It turns out, all right, it turns out that that's as far as you can go. You can actually not factor 4x squared, x squared plus 4x plus 5. further over the reals. So this cannot be reduced. Further. Now, you guys should ask, how on earth do I know that? Right? Like, how do I know that x squared plus 4x plus 5 cannot be factored? Like, how do I know for sure that that cannot be factored into a product of like two things, right? Like, how do I know that? Right? I'm telling you it's true. I have certainly not explained it to you why that's true, right? Can you guys give me an example of another quadratic which cannot be factored? What's that? Examples. Let me give you a simple examples. Simple examples, listen to me. How about this? X squared plus 1. Right? You cannot factor this as a product of two things. It can't be done. Well, so how many of you guys know complex numbers? Do you guys know about complex numbers at all? So to explain to you why it can't be done, it's best for me to show you. To explain to you why it cannot be done over the real numbers, the most simple way for me to explain to you why that is to show you that it can be done over the complex numbers. And because of that, we know it cannot be done over the real numbers. So just to show you, complex numbers have the form a plus ib, right? Where I squared is equal to minus 1. All right? So here, we could write this as x plus I times x minus I, where again this I is the square root of minus 1. So it's not a real number, it's something else. But if you try it out, multiply this out, what do you get? You get x times x, which is x squared, plus ix, right? Minus ix, minus I squared. So see, the cross terms cancel out, right? And so these cancel, right? And what's I squared? Well, I squared is minus 1, right? Which means minus I squared is equal to what? Minus a minus 1, which is also known as 1, right? So this works out to x squared plus 1, which checks, right? So the point here is the factorization of this polynomial, it needs complex numbers, right? So I'll put the result here. X squared plus 1 factors over complex numbers, but not over real numbers. All right? So the rule in here is to use real numbers. All right? Until the very end of the course, there's like a few sections on complex numbers. We'll get back to it, okay? But at the moment, to fully understand polynomials, I have to tell you a little bit about complex numbers, right? And that little bit is just that if the polynomial factors with complex numbers, that means it cannot be factored over the real numbers. All right, so such quadratics are called irreducible or prime. All right, so that's our words for it. So I usually will say irreducible, right? So my claim to you is that x squared plus 4x plus 5 is also irreducible. All right. Let me show you why that is. Why x squared plus 4x plus 5 is irreducible. Here, I'll show you why. So what I'm going to do is something called completing the square. All right? So how do we complete the square? So here's what we do. We take number 1, we write in form x squared plus bx plus c, all right? So first of all, I start by insisting that we have a leading x squared, right? We don't have like 2x squared or 3x squared, right? X squared, all right? Once we have that, we rewrite x squared plus bx plus c as x plus b over 2 squared minus b squared over 4 plus c. That's it. This is all that completing the square is. Just grouping all of the x terms into a square. That's it. All right? So let's apply that to 4x squared plus 4x plus 5. Like step 1 is already done for us, right? So x squared plus 4x plus 5 is equal to what? So here, notice the b is 4. So we take half of 4, which is what? 2. So we do x plus 2 squared, right? Now, we have to subtract b squared over 4. In other words, we have to subtract 4 from this one. See, because b here is 4, so b squared would be 16. 16 divided by 4 would be 4. So we subtract 4, and the c is 5. It's still there. All right? So we have x plus 2 squared minus 4 plus 5. Now, just to emphasize what's going on here, guys, this x plus 2 squared, what would it be if you multiplied it out? We've got x squared plus 4x plus 4, right? So see the logic here of the algebra is to start with, we have this x squared plus 4x, right? And when we write down x plus 2 squared, we have x squared plus 4x plus this other term right here, right? Plus this 4. That 4 was not there to start with, so what do we have to do? We have to subtract it, right? Otherwise, we've added to the expression. So by grouping x squared plus 4x into x plus 2 squared, we capture back the x squared and the 4x, right? But we've also added this term, 4. So to fix it, we subtract 4. This is completing the square. And then the 5 is still there, right? Now, to clean things up just a bit, one more step algebraically. What is this? 5 minus 4 is what? It's 1, right? X plus 2 squared plus 1. See, that's the same pattern as x squared plus 1. We can factor that with complex numbers, but we can't factor it with real numbers. If you guys would like, I can show you the complex factoring. I'll do it this once, all right? This is x plus 2 plus I times x plus 2 minus I. So this factors over the complex numbers, but not over the real numbers. So what I'm telling you here is we can use, actually, this completing the square idea to decide whether or not, oh man, I was going to come back to that. You'll have to remind me later. We can use completing the square to decide whether or not a quadratic polynomial can actually be factored. Some of them can, some of them can't over the real numbers, right? So Let me just tell you the theorem, all right? Actually, rather than telling you the theorem, let me give you 3 examples, and then we'll state the theorem. So example 7, let's try another one of these. Let's do x squared plus 6x plus 2, all right? And I want to complete the square. So what do? I look at this. This is the coefficient of x, right? I take half of this, right? Half of that is what? 3, right? So I do x plus 3 squared. Let's think through this. X plus 3 squared is doing what? It's getting me back x squared. I'll write it out. X plus 3 squared is what? X plus 3 squared is x squared plus, well, write it out. X plus 3 times x plus 3, right? How's that work out? X squared plus 3x, which is 6x, plus 9, right? So what do I have to subtract from x plus 3 squared to get back what I have to start with? Ignoring the 2. Just ignore the 2. So I've got x squared plus 6x, right? I've got it here. I'm writing x plus 3 squared, right? So to be fair, I have to subtract 9. Otherwise, I would be changing the first 2 terms. Subtracting 9 here makes x squared plus 6x equal to x minus 3 squared minus 9. See, because down here I can solve this. I can solve this equation, and I get x plus 3 squared minus 9, right, equal to x squared plus 6x. This is the logic behind completing the square. We're just replacing x plus 6x with a square, all right? And then, of course, we have plus 2. It's still there. Now, that's equal to x plus 3 squared minus 7. Now, there's something I should have told you earlier today, and it's my bad. I meant to say this at the start of class, and I just got carried away with other things. But it is time. It is time for me to emphasize this, all right? This is another important pattern to look for in factoring. It's called the difference of squares. All right, so the pattern is this. If we have a squared minus b squared, we can rewrite that as a plus b times a minus b. So this is like a very important factoring formula. Anytime we have a difference of squares, we can use this formula to factor it. Like here, we've got x plus 3 squared minus 7, right? So if you look at this, you could look at this as a squared minus b squared, where what? A is equal to what? X plus 3, right? What's b equal to? That requires a little bit more imagination. How can you write 7 as a square? Here, how can you write 13 as a square? I'll show you that. 13, written as a square, is the square root of 13 squared. That's the trick. Right, so how do you write 7 as a square? We write it, 7 is equal to the square root of 7 times the square root of 7, right? So we can look at this as b equals to the square root of 7, right? So this x plus 3 squared minus 7, we can write as a plus b times a minus b, right? And how's that work? Well, I need to erase this line here, okay, guys? Because everybody got that one? I'll ask again. Does everyone have this line already? You understand, once we're comfortable with completing the square, we don't have to write this line down either, all right? We can just trust the method, like I wrote over here, you know? Now, I personally, I actually don't think b squared over 4. Like what I actually think, I think about whatever I put here, I subtract the square of it. That's actually how I think through the logic of it. You know, I don't actually usually do the formula b squared over 4. I actually think through it like I'm showing you guys. But what I'm getting to here, what's a plus b, what's a minus b? We've got x plus 3 plus the square root of 7, right? X plus 3 minus the square root of 7. So in this case, this quadratic factored over the reals, right? So it factored. Woohoo! Right? Great. Let's look at another example. What if we had x squared plus, let's say, 10x plus 25? Poor planning on my part. Let me rewrite it. Okay, guys. So you tell me, how do we do complete the square here? X plus what squared? What do I put here? 5. And the funny thing here is then we subtract 5 squared. That's the method. Subtract 5 squared, which is 25, right? So just to emphasize again, I'll use my color coding. These two terms here are equal to these two terms, right? The 25 rides along. I don't do anything to the 25. I just add it again. Of course, the 25 and the 25 do what? They cancel, right? And this one's what? This is just equal to x plus 5 squared, right? Now, you're like, so show of hands, how many people could have factored x squared plus 10x plus 25 using the stuff we talked about last class? I see 1, I see 2. Or was that a hand or was that a red? That was a hand, okay. Sometimes it's hard to, tell the difference between a hand and like a thinking pose, But yes, I mean, could you do this without completing the square? Absolutely, right? But we could also complete the square and see, hey, this is actually a square. Just straight up, it is, right? But anyway, we've also completely factored this polynomial, so there we go. Example 9. Let's look at x squared plus 16x plus 100. All right? So complete the square. What do we got? X plus what? What's half of 16? Half of 16 is what? I heard an 8. So we square that, right? Now, to be fair, I have to subtract 8 squared, right? What is 8 squared? 64. Very good. And I still got the plus 100, right? So what is, 100 minus 64 is what? 36? Yeah? All right. And, okay, so this is going to be my third complex calculation today. I hope you can forgive me. But 36 is 6 squared, right? So I can rewrite this as x plus 8 squared minus 6i squared, where again, I squared is equal to minus 1, right? What do I have? I have the difference of squares. So I can use the difference of squares formula to rewrite this as a plus b times a minus b, right? So identify this as your a squared, here's your b squared, right? And so what you got is you got x plus 8 plus 6i times x plus 8 minus 6i. What does this show? This shows it can be factored over the complex numbers. I mean, you need really more to the point, you need complex numbers to factor it, right? So that means that this cannot be factored over the reals. This is an irreducible polynomial. This shows that it is irreducible. Okay, guys, so question. For which quadratics can you do completing the square? When is it possible to complete the square on a quadratic polynomial? Is there a quadratic polynomial which doesn't allow you to complete the square? I mean, look at this algorithm. All you do is take half of the middle coefficient and square it, right? You can always do this. If the middle coefficient is 0, it's done for you already. Right? Like, for example, x squared minus 4, x squared plus 4. These you don't need to complete the square because the square is already complete. There's nothing to do. And by the way, this can factor difference of squares. X minus 2, x plus 2, x plus 2 times x minus 2. The next one you cannot do over the real numbers. That one is irreducible. You need complex numbers. So my question to you guys is, number one, I'm going to point out, first of all, comment. You can always complete the square. By the way, it's an algorithm. Did you see that? You don't have to guess. You just do. Right? And then what? How do you decide at the end of completing the square whether or not you can factor over the reals? What's the rule? So let's say x squared plus bx plus c factor over the reals. Can you see the pattern yet? How about this? If when you complete the square, get plus positive constant, right? Next to square. And by the square, I mean the x plus whatever squared. Then it is what? Right? When we got a positive constant like this one, x squared plus 4x plus 5, we got plus 1, right? It was irreducible. Example 9. When we did completing the square, we got plus 36, right? This one was irreducible. So after you complete the square, if you get plus a number, that means it's irreducible. On the other hand, what else? If completing the square gives x plus whatever squared, and then minus a number, then it can be factored, right? That's the pattern. And of course, if it's 0, it is already factored as you complete the square. That was example 8, right? Example 8, we completed the square and it factored it for us. Which is kind of cool, right? So question, why do we teach you guys the method of factoring I showed you last class? Why don't we just teach completing the square? It doesn't require guessing. It's an algorithm. It always works. I wish I had an answer for you. I really don't. I don't know why we don't complete. I don't know why we don't emphasize completing the square more in most algebra classes. I think I personally had, for me, when it was taught in my algebra class, I didn't understand what we were doing. It was just this sort of blind algorithm. So I didn't like it because I didn't feel like I understood it. Actually, I personally only really understood completing the square when I took differential equations of all things. So for me, it was even past the calculus sequence when I really appreciated this. But when I did, I was like, oh, this is such a better way to think about quadratics. Now, do you have to complete the square to factor? No, you don't, right? Let's look at some examples. So, now, everything I've been doing has been what? The leading coefficient has been what? It's been 1, right? If the leading coefficient isn't 1, then that makes things uglier, that's for sure. But let's just work another example here. What example number am I on? 12? 13? I'll say 13. I might have skipped one. But so let's see here. Let's contrast the two ways of doing things. So x squared plus 8x plus 7. Can you guys factor this one? Let's say without completing the square to start with, right? I bet you can. And honestly, if you can factor without completing the square, if you just see it, then more power to you, do it, you know? I just want to point out that if for some reason you can't see the way through the factoring like we did, you could fall back on completing the square. It would work. All right, so how many people see what to do here? 8 and 1. But I need these two numbers, whatever I put here, to multiply to give 7, right? So 7 and 1. Plus 7 plus 1, right? So if you see that, great, right? But what if you didn't? Well, if you didn't, you could try completing the square on this one. So we do x squared plus 8x plus 7. So this is x plus what squared? Half of 8 is 4, right? Which then I've got to do what? Subtract 16, right? 4 squared is 16. What's minus 16 plus 7? It's what? It's minus 9, right? So this is x plus 4 squared minus 9. And, well, 9 is what? 9 is what? 9 is 3 squared, right? So we could rewrite this 9 as 3 squared, right? Then we look at it, okay, oh, look, it's again difference of squares. This is a squared minus b squared, right? So we know what to do with difference of squares. It's a minus b times a plus b, right? Which in this case is x plus 4 minus 3, x plus 4 plus 3. Lo and behold, we get back to x plus 1 times x plus 7, right? You know, you might have some other classes where people say things like, well, you can have your truth, I'm going to have my truth. That doesn't work in here. There is the truth, right? I mean, it doesn't matter what method you do. If you do the method correctly, we should get answers we can agree on, right? So what do you guys think? Which is faster? Definitely, the one above is faster if you see it. Totally, hands down, faster, right? But if you're stuck, you could always fall back on completing the square. If you're in doubt about whether or not it can be factored, you can try to complete the square. If you complete the square and you get plus a number, game over, it's irreducible. All right? Does that make sense? So I need to do a kind of ugly calculation for you guys, all right? If you'll bear with me, this will take about 3 minutes, probably. So I need to address the leading coefficient not being 1. All right, so to do this, it's gonna sting a little bit, but we're also going to kind of see the algorithm, if you will, for completing the square for an uglier one along the way here. So suppose we have ax squared plus bx plus c, where a is not equal to 0, and a and b and c are real numbers, all right? So I'm going to start by factoring out a. What's then that give me? X squared plus what? Plus b over a times x plus c over a. then what? Well, I'm going to complete the square. But I'm going to complete the square on the inside. I leave the a outside where it is, and I get x plus b over 2a squared. Then to be fair, I have to subtract b squared over 4a squared. All right? And then, next step, I've got x plus b over 2a squared, right? And I need to make a common denominator of those last two terms. Can you guys tell me how to do that? How do I make the c over a look like the 1 over the, the 4a squared term? Like, how do I get a 4a squared in the denominator? How about I multiply by what? To make a common denominator in this last term, I'm going to multiply by 4a over 4a, right? If I do that, then we'll have a common denominator of 4a squared. And so what I get is minus b squared minus 4ac divided by 4a squared. Right? I factored the minus out, which put the minus on the second term. It was plus originally, but minus times minus gives me plus. That's like why I have to have a minus here, because this minus times minus has to give me back that plus, and there's a minus on the b squared to start with. So given the things we just worked through, can you tell me when it is possible or when it's not possible to factor this quadratic over the reals? So ax squared plus bx plus c can be factored if what? If b squared minus 4ac over 4a squared is what? If I want this to be negative, I need that ratio right there to be positive, right? Because then I'd have minus a positive number. That would be the case that we're like subtracting a negative number. So I would need this to be greater than, and of course equal to 0 is also fine, because that's the case it's a perfect square. I need that, right? But if b squared minus 4ac over 4a squared is less than 0, then ax squared plus bx plus c is irreducible. So can we simplify these conditions? Can you guys tell me, 4a squared, is that a positive or a negative? It's positive, right? So that doesn't affect the overall sign of this at all, right? So I can just go and I can erase the 4a squared, right? Agree? We can just erase the 4a squared. We can say, oh, well, really, it's just if b squared minus 4ac is greater than or equal to 0, or if b squared minus 4ac is less than 0, right? So definition, for ax squared plus bx plus c, the quantity b squared minus 4ac is called the discriminant. The reason for that is it discriminates what kind of quadratic you have, whether it's irreducible or not. So we can decide whether or not we can factor some quadratics by just looking at that quantity. We don't even have to complete the square. If we just look at that quantity, we can decide whether or not they can be factored. I let you guys have a note card or a page of notes on the test, right? This probably belongs in there, right? So here, let's look at some. Example 14, 2x squared plus 3x minus 2. Let's decide whether or not that can be factored. So what do we got? We've got a equals to 2, b equals to 3, c equals to minus 2. What's the discriminant? 9, right, 3 squared minus what? 4 times 2 times minus 2. That's 9 plus what? 9 plus 16? I think we got 25, right? So what does that say? That says it can be factored. We can factor this, all right? So that tells me it's greater than or equal to 0, right? So it says, yep, we can factor it. We might not want to, but we can, right? Now let's look at example 5 here. How about 3x squared plus 2x plus, I don't know, 50. So for this one, what's the discriminant? So I would point out to you a equals to 3, b equals to 2, c equals to 50, right? So b squared minus 4ac is equal to what? 4 minus 4 times 3 times 50. That's what's 150 times 4? It's what? 600? So what's 4 minus 600? It's a pretty big negative number is what it is, right? Minus 596. This is less than 0. This tells me that 3x squared plus 2x plus 50 cannot be factored over the reals. Now, your homework never says over the reals. Nowhere have I seen that appear, but that's the implicit understanding. All right? On your test, I will probably say cannot be factored over the reals. All right, just to be like mathematically precise, but just to warn you, in your homework it just says, you know, can it be factored? Right? It's always the assumption that we're talking about over the reals. Except much later in the course in like chapter 7, there's some complex problems, right? But okay, so great. We know 3x squared plus 2x plus 50 cannot be factored. But what about 2x squared plus 3x minus 2? How are we going to factor that? Do you guys have any ideas? How are we going to factor that one? Let's do it. So the, example 4 continued. How did I get back to example 4? Oh, good. That was 14, huh? Oh, man. What? My brain skipped or something. All right, so example 15 continued. 14 continued. All right, so we got 2x squared plus 3x minus 2, right? There are various strategies for factoring things like this, right? I'm going to use completing the square. And then we'll try something else. So so the completing the square I showed you, right? We had to have what? We had to have x squared out front, right? So how do we make x squared be out front? Well, what we got to do is factor out that 2. Get the 2 out of the way. And then that's going to make things ugly. All right, it's going to. But here it is, 2 times x squared plus, and this is where it gets ugly, 3 halves, fraction. Oh no, oh no. And then minus 1. Now, what I have in parentheses, we can do our completing the square thing too, right? So we have to take half. What's half of 3 halves? 3/4, right? So we do 2 times x plus 3/4 squared, right? And then we do what? We subtract 3/4 squared, right? What is 3/4 squared? Sidebar. 3/4 times 3/4 is what? 9/16, right? So I have to subtract 9/16, and I've still got the minus 1, right? So here's a trick. 1 is equal to 16 over 16, right? So if you think about minus 9 minus 1, that's really the same as minus 9 minus 16 over 16, right? In other words, the constant that we're looking at simplifies to 25/16, which is actually kind of pretty if you think about it, because that's a square. Can you guys tell me how 25/16 is a square? 25 is what? 5 times 5, right? 16. So my point to you is we could rewrite this as 2 times x plus 3/4 squared minus 5/4 squared. Now what do? This is the difference of squares, right? So we look at this as a squared minus b squared, and we write it as what? A minus b? Or did I do? I forget which one I did first. I did a plus b times a minus b. It doesn't really matter which one you write first. Just make sure you don't write the same thing twice, right? And that is what? That is twice x plus 3/4 plus 5/4 times x plus 3/4 minus 5/4. So what do we got? We got 3 plus 5, which is 8. What's 8/4? 8/4 is 2, right? So the first factor here gives us a 2. How about the second one? What's 3/4 minus 5/4? Well, that's minus 2/4, which is, I think that's minus a half, right? So we have x minus a half. And there you go. We factored it as claimed. Not too pretty, but that's, if you understand the completing the square algorithm, you can do these. You need not get lost, right? Now, were any of you guys remember high school, you were taught a different way to factor these sorts of things? Anybody? There is this slide to the side method. I'm not going to teach that to you guys because I don't understand it. That's not true. I understood it last year, and then I became disgusted with it. But to be fair, other instructors teach it because they believe it's the only way that students can factor these things. Maybe that's true for some students. I don't know. If you already know slide to the side and you want to use it, I will not critique your middle work. Like if you write things that are mathematically incorrect and come to the correct answer, you know, I don't assume you're cheating. I assume for this kind of problem, I assume you use the slide to the side thing. So if you would like to see me suffering through slide to the side, you can watch videos from last year. I talked about it in there, but I will talk about the guess and check method for this sort of thing. Let's see if we can do it. I think we'll be able to do it because we know the answer. So example 14 again. 2x squared plus 3x minus 2. So if you were to try to guess and check here, what would you do? What you'd do is like take the 2x squared and write it as something like, you try something, right? You do this one, I would try 2x and x like that, right? Because you got to get back 2x squared, right? So now if you had a problem that was like 6x squared, then you'd be faced with difficulty, right? Because you'd have to decide, I mean, just to show you another one. If you had like 6x squared, then the question would be, do you do 2x, plus stuff. So would you do like 2x and then 3x, or would you do 6x, then x? I mean, this kind of thing, you'd have choices, right? But when I have 2x squared, I'm kind of forced to do 2x and x, you know? Okay, that's not really true, because you could also do square root of 2x and square root of 2x. But the fact of the matter is, the book doesn't give you these problems. I'm just saying logically it's there. I'll shut up. So you guys tell me, I need to get a minus 2, right? How can I get a minus 2? Minus 2 times 1, right? Or 2 times minus 1. Those are kind of the hopeful choices, right? So what are we going to put where? What did you say? Two, the plus 1 to start with? And the minus 2 over here? Ooh, we chose poorly, because 2 times minus 2 gives me minus 4, and I can only add an x. I get a minus 3x. Ah, shnikes. So that's easy enough to fix. We put the plus over here, and we put the minus over here. Now we're in business, because 2 times 2 is 4. Minus 1, 4 minus 1, 3. We're good to go. Is that the same answer? We got the x, you see the x plus 2, right? But you got 2x minus 1. How can you rewrite 2x minus 1? Well, factor out 2, right? When you factor 2 out of this, you get what? You get x minus a half, yeah? So they are the same answer. As I said, there's not two truths in here. There's the truth. Does that make sense? Okay, let's do some more examples, because I've spent an awful lot of the bandwidth today on what cannot be done, right? But it needs to be addressed, right? Because, you know, tell you what, let's do something shockingly easy compared to what we've been doing. All right, so minus 5y minus 10. Factor something out. What should we factor out? How about a minus 10? I'll take a minus 5. I mean, you could pick out whatever you want, but minus 5 is a good choice, because then we get a y. And how do I get minus 10 times 5? I mean, how do I get minus 10 from minus 5? Yeah, plus 2. Y plus 2. There you go. There are problems like that in your homework. That's like number 7 from section 4.3. Let's see here. Example 17. Minus 5a to the 4th plus 10a minus 20. And it just says factor out with a negative coefficient. Factor out with a negative coefficient. That's not very good grammar. So I think we'll factor, man, these, I picked two problems that are the same. We're going to factor out a minus 5 again. Right? So I'll do the easy part, a to the 4th. How do I get 10a from that? Minus 5 times what gives me 10a? I need a 2. I heard a 2a. That's not going to quite work. We need a plus 10a, right? So we need to minus 2a, right? Because minus 2a times minus 5 gives me 10a. How do I get 20, minus 20 from product, yeah, a 4, right? So plus 4. Now, there you go. Now, you could ask the question, can this be factored? So, can this be factored? Oof. That's a formidable question. The answer is, I'm not sure. I mean, well, excuse me, let me restate that. I know for sure it can be factored. Any real any real polynomial can be factored into a product of irreducible quadratics and linear factors, both of those possibly repeated. So it's always possible to break down a 4th order polynomial into a product of things. However, that possibility doesn't mean